Yeah, I should mention that the scheduled talk for today was a continuation of what happened before the Big Bang. That got or it will be rescheduled in the coming one of the Saturdays in September probably, but the specific date has not been decided yet. So I'm just filling in the gap here. So, and we had a lot of discussions on classical, on configurations related to classical mechanics. So I thought we should take a small leap here, a big leap, I guess, and do some quantum mechanics. But I'll talk very straightforward, simple things, which is one of the very popular statement in quantum mechanics is that measurement disturbs the system. And what will be slightly different here will be the notation I use. And that otherwise it should be very straightforward, standard textbook stuff, but hopefully that helps connect. Often you will hear the statement that the best language for doing the quantum algebra is vector spaces. So this is using the idea of vector spaces in a more explicit manner. So that's the way I would give the abstract of the talk. So this is I'm going to talk about measurement disturbs system, but more relevantly measurement and interaction, like what's the connection between the two? Or is there any connection at all? So often we say that if we want to measure something, we need to interact with the system, correct? There is a sensor. So there is a sensor has to interact with the system, and that itself disturbs the system in a sense. So in a sense, that's what we're talking about. But I'll bring out something non-trivial in here, and that's what the standard quantum mechanics is. That so the statement will be that every measurement involves a interaction, but interaction in itself does not imply a measurement. So that's a statement that will come out eventually. But let's proceed and let me develop some necessary tools for this. So, but before that, let me introduce something, an experiment, just so that we have. So this is called a Stern-Gerlach experiment. This is not necessary for the talk, but often it helps to have an intuition for what's happening. So if you don't want a mathematical language, if you really want to see something happening in front of you, or at least visualize it. So this is everything that I talk can be interpreted in terms of this setup. So what is Stern-Gerlach experiment? So let's say so that is a chamber. Let's say so that is a chamber of silver atoms. So there's a lot of silver atoms in here. So this is silver atoms, and silver atoms has this property that they have a magnetic moment. So each silver atom behaves like a magnet. That's what we want to keep in our mind. And there is also, if you want the details, so the magnet will be the magnetic property of the silver atom will be represented by what is called the magnetic moment.
It has a permanent magnetic moment, Shajesh?
Yes.
Nice.
Yes. Yeah. And
what kind of magnet is it? Do you know?
You mean diamagnetic or
Yeah,
paramagnetic?
The properties, yeah.
So this is from the orbital momentum, I would think. Diamagnetic, I suppose. I'm not sure. I would think diamagnetic, because this is probably coming from the electrons movement going around the nucleus. So there's an electron going around in orbit, so it deals with current. So so the question is, in what sense does this have a magnetic moment? If you think of a magnet, and if we have some experience in electrodynamics or magnetism, we always associate all magnetic effects to current. So somewhere there must be a current going around in circles, and that's because there are magnetic monopoles. And here we are imagining that inside an atom there is an electron going around in circles. On the other hand, a proton is at least going in very small circles if it exists at all, and that contributes to this magnetic moment. And most of the atoms do have magnetic moments due to that reason. Like most of the atoms and molecules typically have. On the other hand, electric dipole moment is not very common. In fact, elementary particles most of the times do not have.
Like I think I just found it interesting because I never thought that silver. I never tried a magnet, like picking up a silver with magnet. But
yeah. And there is this, and again, when we think of a magnetic moment in the elementary introductory physics courses, so I already said that there has to be a current going around. So here the current is going in circle, and that seems to suggest that there is an angular momentum. So something going in a circle associates an angular momentum to that. And the connection between the magnetic moment and the angular momentum is the charge Q over 2 times m times the angular momentum. So whatever we are talking about is either related to the angular momentum or the magnetic moment. Often when you're doing quantum mechanics, you think of it as a property associated with angular momentum, right? So in this sense, when the atom is even at rest, it has an angular momentum, and then you take it to the quantum nature of this is that you bring out the spin associated with the system in this sense. So whatever we are going to talk about is, or at least in this setup, is related to angular momentum. So there are a lot of magnets. The way we want to think of it is that there is a chamber, there is a box, there is a lot of atoms, and each of them has a magnetic moment, which is decided by the orientation of the atom in space, since they are not all oriented in the same direction. So they are all randomly oriented in a direction. You heat this up, right? So they are all going fast enough, and then make a small hole in that small tiny box, and they will start coming out in all directions. So put a collimator in between, just basically a metal sheet with a hole in it, and only few of them that's going in that direction come out, and put another hole in that, and suddenly you have a beam. So now you have a beam of silver atoms, still not oriented in the sense they could be in its magnetic moment could be in all directions. They have a velocity that's going in that direction. In that sense, it's a beam. But each of the atoms in itself could have their magnetic moment oriented in any direction in space. So that's the initial setup of the beam. The arrow suggests that they are going to the right, and then you put it in put this in a magnetic field. That's a north pole and a south pole, and I represent the north pole with a point and a south pole in this manner, just to point out that this magnetic field is not uniform. So the magnetic field, whenever there is a pointed object, the fields are stronger there, and this is how magnetic field looks like. Again, not really relevant for our purpose. And in this magnetic field, this magnet tries to orient itself. We are all familiar that if you bring in one magnet close to another magnet, that tries to orient itself. And because there is this inhomogeneous or the gradient of the magnetic field, that means the magnetic field is stronger here and weaker here, they also tend to get attracted towards the North Pole if the North Pole was pointing this way, right? or if the North Pole is pointing this way, repel and it will go down. So it can go up or down. And the idea is that this can go either this way or that way. Just for our purposes, we won't go into the details in here. This is again interaction between the magnetic field here. The magnetic field will be represented by B, and these magnets is minus mu dotted with B. And often you say this is the energy, or sometimes you say it's a Hamiltonian, right? I won't be using any of this, but this is, as I said, I have an intuition of what's happening. Okay, so that is this. The main idea is that let me mute. Got muted. I think it's all good. Okay, sorry. Yeah. So we have a lot of a lot of atoms. Lot means 10 raised to 23 of them, and as a magnetic field, they go up or down based on the initial orientation. Is it bent towards that or this? And the idea is that you should see and these are silver atoms. Silver atom has this feature that they will, if you have a photographic plate, if you remember your olden days, you had if you want to take a picture, you basically expose silver atoms to that. So what one used to do is that there will be a film, and a light will expose that, and then you make it interact with the silver atom, so that silver atoms will blacken out whatever was exposed to light. So basically silver atoms on a photographic plate will make a distinct mark. And it was noticed that it either goes up down here and either goes down here. That was not what was expected, because you would have, the magnetic moment is oriented in all direction, and when you take a dot product, that is a cosine theta, and depending on what angle it makes, you should have got all over the place. So this is what was experimentally found. There are two distinct spots, and this was what was expected. So there should have been a whole line of atoms out there, and this was what was theoretically expected. So when you expose it, there should have been a straight line, or if this was, I mean, this is having a geometry there, so that's what brings it out, line instead of circle. There. The main idea you want to take home is that this was what was expected, but instead you have this two-state system. So that's, and you will see that there's a statement of quantization. Quantization means the name quantum comes from the fact that these are two states instead of a continuous state. And this is a quantization of the magnetic moment, which is in turn that angular moment. The way we want to see this, so I'm going to make this, I want a notation in here. So this is, this whole setup will be thought of as a single straight line. Here there is a magnetic field, so that's my magnet. So that's my magnet P, and since it comes out as up and down, I want to think of this as 1 and this as 2. So let me say this is 1 and that's 2. And here we have let's say disoriented in the sense that it is not oriented atoms. And so basically there is a source of
John has a question. You have to speak.
Yeah,
John.
sorry, I was waiting for
yeah, please.
a break. So you said that L is angular orbital momentum, so it could occupy depending on what shell it's at. And I'm assuming that I think silver has it's a big nucleus, so it has like more than 2 values. So you're,
Yeah. So maybe I should emphasize here. So what kind of L it is? L here will be the spin. So this is h bar over 2. Like this will come out to be sigma. This is a definition of spin if you want, and that's a quantum effect there. So this is not really the yeah, go ahead.
so I guess from an earlier question, we said that the magnetic moment was due to the orbital.
Yeah. So in what sense did this become a
And then,
spin
yeah.
of the electron itself, right? Yeah, good point.
So maybe it's just-
So maybe the point is, what I should say is that I want to say this is J. In general, this is J and J. So this is your S, I guess. Right, and J will be L plus S. And I guess we want to talk about the extreme situation where L is 0, right? And what I gather is that the silver atoms, the orbital angular momentum is 0. So in that sense, probably what I said, the motion of the electrons is not contributing to this magnetic moment. It is probably the protons itself that is contributing. Not sure. Yeah, anyone else wants to add something to that?
Yeah, I think it's in the silver atom, you have 47 electrons. And this is the spin angular momentum of the unpaired 47th electron, just that.
Just the 47th. So rest everyone kind of balances out.
Because they are parallel, anti-parallel, so they cancel out. So this is the unpaired one. And that in that sense, this is paramagnetic, because diamagnetic is when you have even number of when all the pairs cancel, then it's a diamagnetic material. When you have a unpaired electron, then it's a paramagnetic. So what Prati has asked, this is actually paramagnetic.
Okay.
This is unpaired 47th electron for silver.
Yeah, let me not. Yeah, I don't know. So to answer John's question or Prati's question. Yeah.
I hope I understood the John's question, that what is this?
Yes.
Yeah, due to, right?
Correct. Exactly. Now his point was that if I interpret this as electrons going around, then you're talking about the orbital angular momentum, but this is coming from the spin itself, in a sense. Yeah.
So yeah, this is actually coming purely from the spin and not the orbital part.
Yeah. Does that satisfy you?
Yeah, I mean, definitely.
Yeah.
Everything's.
Yeah, the best I can say is that it is not going to influence whatever our discussion as that is going to follow.
Yeah, that was,
Okay. Yeah. So that's the only thing. So the point was that how can this be two-state if it is a higher angular momentum that could be multiplied? And I should say that you can do this experiment with a higher angular momentum also, so that can be 3 or 5 or so on. Okay. So the way I want to look at this setup is, again, for visualization, is that there is a source, then there is an interaction. So this will be called an interaction. Remember, I said I would like to distinguish or tell something specific about measurement and interaction. So there is an interaction, and there is an observer here. And the observer has this choice. At this point, this is just, there are 2 points that is coming in, and that means there is no measurement made at all. But now you can come in and say that I'm going to block this state since there are these two states that separately go in. And I have the choice that I just bring in a metallic sheet and put it in front of this beam of the beam that goes out. So that's a selection you make. When you reach here, either I have the choice of making the top part of the beam, those that got deflected upwards in this on this blackboard diagram. So that will be called, suppose I select the top, so that I'll represent that as a bar. So for example, this I'm closing now, right? If I close this, so this will be called a measurement. And that's the notation I'm going to use. So I have a choice of having this beam coming out. I can have the opposite. So this is one choice possible. I could also have this. Right? And I could also have both together. And when I have both tick marks together, that will mean that there is no measurement. So this is a measurement now. Otherwise, the interaction was happening, but I didn't bother to find out how many were going up and how many were going down. So only when I actually look into it, I know that how many have gone up and gone down. So, and I would like to, or we will try to bring in some non-trivial conclusion between the two. So that's the notation. Okay. So now I want to bring in some algebra associated with it. So I'm going to introduce the same diagram, but with something more specific, and I'll bring in vectors for that purpose. Any questions at this stage, especially between this measurement? Is there any confusion what I meant there? I can block this, I can block that, or I can block both. Or block, sorry. Oh.
I mean, why can't blocking be seen as an interaction? Because, okay, let's just say you don't measure immediately after. So I think this, like when you have the beam, like that is the measurement because you're getting data. But I mean, as far as like the atoms are concerned, if you just block them, you're not measuring. Like you're not getting information about the system. So
yeah, you're saying that, oh, this is also an interaction. Agreed. But I'm going to differentiate. So this is what, or maybe I want to specify what I meant by measurement here. So I'm going to say when I block this, that means, or I'm selecting. So instead of measurements, let me call it selection. That's probably a better. So I'm selecting a beam out of this. That's what I mean. So I'm going to differentiate the two. It is possible that they go and I do not make a selection, or I make a selection. And when I make a selection, I have two choices. And the point is, can you get something non-trivial out of this simple setup, right? Or the idea is that whether I make a measurement or don't make a measurement, should something change? Because anyways, this is going through a magnet, who cares? Like how many atoms come here should not matter, one would think, based on whether I stop this or not, because it has already happened. Correct. So this distribution has already happened. Whether I measure this or not, that's not supposed to affect that how many atoms went there. But that's not what we will see. We will see that when I make the selection, in a certain sense, it will affect that. Okay. So that's just to give you a feel for what I'm going to come at. But for now, there is an interaction and there is a measurement or selection process, and selection can be made. I choose the top beam, bottom beam, or I just don't select at all. So that will be the options available, and that's the setup. Right. Okay, and I want to bring in the mathematics for this, and we all study vectors. So I'm going to use the idea of vectors for doing this. So this is the vectors, or let's say vector. There's a vector A. And we have a diagram. So typically, vector is just so that's my vector. It is it's a physical quantity that is oriented in space. Let me stick to 2 dimensions. That means everything is happening on this blackboard. So that's it. So there is a length of this vector is a magnitude of the vector, and it has a direction. That's the idea of a vector. But often we are used to having a basis, and that means we have an axis associated with this. So that's your axis. And let me call this axis to be E1 and E2. So in that context, so that means that is what is the length along this direction, what's the length along that direction, and this is often written as E1. So this means that there is so much length along this direction plus so much in the other direction. So that's your idea of a vector. We could have chosen another basis also, but let's bring a few properties that led to this vector, and that's what we will use. One is that is what is called completeness relation. And using this vector idea, we will write that as E1. So notice these are 2 vectors, but this is not a dot product. This is not a cross product. In fact, this is an outer product. So every time I write E1, that means this is the outer product. But I'll stop writing the outer product and just write it as E1. So whenever there is no dot product or a cross product, it means that it is in principle it's a tensor, or often we say it's a dyadic, right? So that means it's a double vector in a sense. Plus E2. And if you were to do this algebra with vectors, this comes out to be just an identity matrix, if you want. So that's a dyadic, or that's a tensor. So that's a unit tensor, if you want, right? So and this also has this feature that we will associate. It's good to think of it in one more way. So notice that E1 as a single piece dotted with a vector, right? So I simply have this piece out of it. The identity involves 2 pieces. If I were to take this, E1 dotted with A is what is defined as your X component. So this is E1, A1. So in that sense, this is a projection operator acting on A. So this piece has this interpretation that it projects the vector A along the direction of E1. The same thing with E2 also, that will project it in that direction. I'll mention that again in a second. There's also orthogonality. Maybe I used that already there, so I shouldn't have. I went a little fast there. The projection was not obvious there. So orthogonality is that the 4 of them, E1, now there is a dot product, the usual dot product between vectors. We'll say this is just by looking at the diagram, because that's E1 dotted with E1 is 1. I can have E2 dotted with E1, that would be 0. That means it's orthogonal, and E1 dotted with E2 would be 0, and E2 is equal to 1. So that's a orthogonality relation. And third is what I meant by projection operators. And we have the idea that E1 E1 dotted with A, the vector A, this is, now we have to use the fact that E1 dotted with E2 is 0. And if I use this especially, this means that this is E1 times A1. There's also E2 dotted with A is equal to E2. And what will be very important in our discussion is the fact that it is obvious in this way of looking at it, that E2 dotted with A, since this together, so that means I project both along the E1 direction and project it along the E2 direction with these two. If you want to think of it as operators, then it's just identity. I get the vector itself. Right? This is identity acting on A. That's the vector A itself. Okay. So I can, so this is when I say selection, right? So what I'm going to do is that selection along this direction, selection along this direction. And when I do not select, basically I'm doing this. So that's what the interpretation, or that's how I'll do the mathematics in there. So let me go back and connect this vector ideas with what we said earlier. And before that, any questions on this part, on the vectors? Right, the only new thing should be this, or slightly unfamiliar might be this idea that as a completeness statement, which gives you. Okay. Okay.
Shajesh, just for, I mean,
Yeah.
somebody watching this later who may be familiar with the standard, the bracket notation in quantum
Correct.
mechanics. So this is nothing but the I mean, the
Right.
outer product is nothing but in the bracket notation. It's just the kate, the kate which are facing the opposite, the kate and the bra. And
Correct. Correct. So if you would like it, that's a good point to bring out. So this can be thought of like this,
yeah, exactly.
right? And you're good, right? And
Yeah.
then this is, so now you need a notation for this. Schwinger would write this as this. Right? So
Yeah.
I think he tried to, or without that one, right? And without ones and all. So he tried to.
So this is just
do that.
connecting for those people who are maybe familiar with that notation.
Right.
So
No.
this is exactly
very
similar
useful.
thing. Yeah.
Yeah, very useful. Necessary, I would say. And this one, when I'm taking, so this is an outer product, and this is an inner product, and
Yes.
that will involve this. Right. So good point.
Also, just one point.
Yeah.
Not exactly relevant to this discussion, but like when one defines the vector space, so this norm is an additional structure added to the vector space. One can have vectors without defining the norms.
Correct.
This is
Correct. So yeah, that is a
additional
whole
structure. Yeah.
Yes. Yeah. And I'm doing it as a user. How about that? Yeah. So that is, one has to develop all the axioms associated with that. So this is, I'm directly jumping into pretending vectors is no. Yeah.
Norm
Good point.
space,
Yeah. So these are the points I will use. How about that? That's the way to. Okay. Any other comments or questions?
Just I think it's an outlier. Is orthogonality necessary, or?
Yes, because in the projection I used that feature, right? So if it was not orthogonal, then this cannot come out in this manner. Is it necessary? You mean to say, can I deal with
Yeah, it's not relevant, so we can think about that later. Yeah.
Yeah, how important is, not sure. Yeah, I think, yeah. I mean, it can be developed the other way. I can see that. I mean, we have done that this summer, if you remember, but yeah, let me not comment on it. I don't know. That's a simpler way of saying it. Yeah, good point.
Yeah, that's fine. Yes.
Yeah.
I said it was not relevant.
Yeah, yeah. Okay, so so I want to tell whatever we did, or the notation we developed earlier. So we had a configuration where I had a magnetic field. So this will be E1. So I can either select the top or E2. So this is what a magnet does. So a magnet can either, there is a beam coming in and it can go up and down. I'm going to think of it as a projection. So what the magnet does is that it takes a projection operator and projects it on what? So there is a source to begin with. I should have some orientation. It could be a vector A, right? So there is a vector A that comes in, and the magnet basically interacts with it. So this magnet constitutes of two states or two operators, if you want. It can either make it project it in along E1 or project it along E2. And if I don't make any measurements, I have the choice of bringing it in either one of the states. But now I ask, how many of you are there in E1, right? So that's an observer, right? So there is a source, there is an observer, and now I have to define what this would mean, right? So let's say, so I'm going to define what is called a probability amplitude. So there's A, that's, how should I get rid of this ambiguity there? That's the probability amplitude. PA, so PA, so this is probability amplitude. So that will be defined as you have a vector A, and then I project it with one of them. So that's where the selection processes come in. So I have to decide which one I'm selecting, right? So let me, for specificity, let me select the top. If I do not select, then that decides this operator. So this is, I'm selecting. This is E1. And then you would of course say, well, why is that selection important? If I do not select it, then that means both are tick marked, and that's a 1 there. And we'll say that there's a distinction. And then I ask, how many of these atoms that come in here are along the first, along the direction of E1, and that would be this. And this is clearly a 1. And I would also like to normalize this so that we can have the idea of a probability distribution in here. So let's make this a hat. Let's say this is a hat. So let me divide that out. And then you have A1 over A1 square plus A2 square. I'm going to normalize that very soon. That's just for discussion here. The probability itself will be the square of the probability amplitude, and you square that quantity. So that's going to be our mathematical input here. So there is a state, we project it up and down, and then we ask how many are there in that. And I'm going to distinguish based on the selection process, can we get something non-trivial out of that. Notice once I have this beam, I can put another setup here, so I can do a Stern-Gerlach setup in series, and that's exactly what we want to do. So let's begin with E1 itself instead of having this vector A. Let's have this vector E1 to begin with. So I have already done this selection process if you want. So I have an E1 and I'm putting in a series Stern-Gerlach. So let's have a setup where there is E1. I have E1, E1, E2, E2, and then I make a selection here. And let me ask, this is E1. So that's one question you can ask. And let's see how many possibilities there are, right? So let's say this is again E1, E1. I will always keep E1 the same on the other end. And I can have this the same, but now I can ask how many are there in E2 state. And do the same thing, E1, 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 E2, 2. This time I close the top and ask there are how many E1s. And 2. And now that I am working with E1 and E2, I can go up. Let me bring.
Shajesh, so
Yeah.
whenever I was learning this stuff, like it always was very confusing for me. Is it possible somehow to give an analogy of a coin flip here? Like I always found like, oh, okay, why it is probability is a square of the probability amplitude instead of like just being half and half. The situation now you are explaining it, I understand. Now I understand in the hindsight stuff. But suppose a student comes and he only knows probability that you can flip a coin, it can have heads or a tail. And how do you say that the probability will be 1/4, not 1/2? There is a selection process, right? That is what you're trying to explain in the. Is there an analogy, or we cannot give any kind of analogy there?
I cannot think of a coin flip example, but in interference of light, I can think of the amplitude is important, right? First comes the electric field, and then the square of something is what is measured. So that I can see, but coin flip, I cannot think of. I would think there isn't one, but I don't want to make that statement. Yeah. Yeah. Like probability there is just one, and we are only talking about the result, right? We are not asking what is causing the flip. Why is there a possibility of so much? There it is just the result. Like there we only measure this quantity. Yeah. So
I mean,
I
that's
don't know. I don't know.
Yeah, that's fine.
Yeah. Okay, so this is should be straightforward in a sense that this is almost like a check, right? So this is like coming from here, right? I've selected this beam, and then I'm asking, I am again making a selection along that direction. That should come out to be 1. So this is almost like acting like a check. So this will be in our notation. I start with E1, dotted with E1, E1, dotted with E1, and that's 1. And probability is 1. Square that, and that comes out 1. Do the same thing here. So that's E1 dotted with E1, 1 dotted with E2. So that's 0. That's probability is 0. This is selecting E2 now. Dotted with E1. That's 0 again. that probability is 0. So this is E2 dot with E2. So that's equal to 0. That's probability is 0. This is basically a checking on that. If you select this beam, of course, after you select it again, it should reproduce that, right? Now that I have this, it is good to bring in. So this is all. This line, remember, represented a magnet. So that's the interaction, and this was a selection. So this involves a selection process, but there is also this possibility that I do not select. So let me draw a line here. So these are all interactions with selections, but I can always have two more situations where I do not make a selection. That means I allow both of them to come in. And then there is E1. And in this case, since I do not make any selection, that's just identity, right? So this is E1. That means no selection. So that means it's just 1. That's 1, and that's E is equal to 1. Everything is consistent. So this is E1. Do the same thing. E2, E2. And again, no selection, but this time require what is 2. And 1, 1. After the E2 this time, that's 0, and P is equal to 0. Right. So that's your overall picture. Again, straightforward, simple. This is all we have a state already in a basis in which you're measuring if you want, and you get this. So this is all should be fine. Nothing surprising happen here, especially when you look at it in this terms. This is all vector ideas of vector. But now let's do something slightly different. Let's not have this basis at all. We choose another basis. Okay. Any questions before I go into that? This was just a check in a sense. If I have this, or my senses are the calibration, if you want, in a sense. So now we will do something different. Basically, we use another basis vector. So let's have a new basis, and let me draw that basis in this tiny space I have here. So this was my original basis. So that's E1, that's E2. And now I rotate this a little bit. And this is G1. And that's G2. And let's have an angle theta associated, angle theta between that. For all, if you want to think of actual numbers instead of a variable, think of theta as 45 degrees, and that gives you a specific number to work with if you would like that. A general vector here is A, and it can be projected in E1 basis or in G1 basis. Both satisfy the same ideas of completeness relation and orthogonality. Everything goes through. Okay. So now let's ask the question that, so five minutes, maybe if you go by the time. So now let's say again I start from E1 here. So this is, let's say that I have a comparison with the one on the other board. So I already have a Stern-Gerlach setup. Already the beam has been selected in E1, and then I put in a magnetic field if you want. And this time I orient it in a different direction so that it brings it, projects it in different directions. And this time I say this is G1, G1, and G2, G2. And again, selected, but when I'm selecting it, I go back to my original basis. Right, so that's my E1. So I ask, I have a beam coming in a certain direction, then the magnetic field is not really in that direction. It is actually rotated off a little, and they will distribute it into the top and bottom with respect to that magnetic field. And then I again select, let's say this is selected, and I ask how many of them are still in the E1 direction. So in principle, to do this, you need 3 Stern-Gell setups. This one acts like a source. You create the beam. This one is, in a sense, doing the measurement. And here, this is the observer. I give 3 different names, but all of them are interactions, actual interactions between the magnetic field and that. So it's just that I've given different names: source, interaction, and observer. And then the probability amplitude this time would be E1 dotted with G1, G1 dotted with E1. And let's have the diagram here is still available. So that is E1 dotted with G1, that's cosine theta. So that's cosine square theta that's coming in here. And if theta was 45 degrees, that's 1/2, right? But we are interested in probability. This is probability amplitude. Probability will be cosine 4 theta. Right? The 4th power of that, and that will be 1/4, right? If theta was equal to 45 degrees, that's 1/2, and that's 1/4. Do the same table here also. This E1, G1, G1, G2, G2. And this is E2 this time. Probability amplitude is E1, G1, G1, that's a selected, but then eventually you're projecting it along E2 direction. And this time it is E1 dotted with G1, that's cosine theta. G1 dotted with E2, G1 dotted with E2, so that's cosine of 90 minus theta, so that's sine theta. But if it is 45 degrees, it is still 1/√2, 1/√2, so that will still be 1/4. But in terms of this angle, so this is cosine square theta, sine square theta. Like that's the probability. Do the same thing. G1, G1, G2, G2. This time select the bottom and then observe it along E1. Probability amplitude is E1, G2, G2 this time. E1. So that's E1 dotted with G2. E1 dotted with G2 is cosine of 90 plus theta. So that's minus sine theta, and this is sine square theta. The probability will be sine raised to 4 theta, and do the same thing once more, right? So this is all with selection. G1, E1, E2, E2, E2. And this will be E1, E2, E2 dotted with E2. E1 dotted with G2 was minus sine theta, and E2 dotted with G2 is cosine theta. Remember, probability is the magnitude of the probability amplitude square, or if you want complex conjugate, if they were complex quantities, then this is again sine square theta cosine square. Clearly, if you were to add up all these probabilities, they do come out to be 1, right? Cosine 4 theta. So the total probability is cosine square theta plus sine square theta square, right? Which is indeed 1. It will always be 1, but that's yeah, that's a check if you want. But again, all this involves selection, right? We are making, so there is an interaction, we are actually selecting. But I said we should, I'll bring up something when you do not select. So this is all with the selection. What if I do not select? So this is E1 and this is G1, E1, G2, E2. And this time no selection, which means that I allow both beams to come in, and that's 1 again. So and I select one of this. So this is E1, G1, E2, E2. No selection, and there are 2 possibilities. But this time either I can do this add up the 2 amplitudes, but I know that this is 1, so this is basically E1 divided with 1 times E1, that's equal to 1. And this is E1 divided with 1 divided with E2, so that's equal to 0. Here, the probability is 1. Here, the probability is 0. Notice, so basically, if you want to take home what is going on, so you want to concentrate only on this, and so let's say this piece here, and the top piece there. If you compare these 2 elements alone, you will see that in this case, you're making a selection. And in this case, you're not making a selection. And the probability has changed. Think of theta is equal to 45 degrees. And then the probability is 1/4. Just because you peeped into the beam, your probability has changed, right? And how's that possible? That should be, that's the counterintuitive nature of quantum mechanics. And that's the statement that measurement disturbs the selection. By measurement, I mean the selection of a beam disturbed my result, right? And that's what I wanted to bring out. And I think I like David Bohm's statement in this, that he, I think it's almost a quote, is that if you have so this is an interaction. If you have an interaction, it doesn't guarantee an observation. But if you have an observation, of course, it requires an interaction to have happened. But just because an interaction has happened, that doesn't guarantee that what kind of results will come out. Again, think of the magnetic field, that just things are going anywhere through that. But you come and block one of the beam, and suddenly the result on the other side has changed. So that's counterintuitive, I believe. Yeah. So that's all. That's fine. That's what I want to point out. Questions?
Shajesh,
Yeah.
I just want to understand the. Okay, so you have when you say you have started with E1, so you have selected the E1 component. And when you say that now, you have this G1, G1 and G2, G2. So you are essentially making the E1 beam pass through a Stern-Gerlach experiment, which is oriented at an angle theta with respect to the original E1, am I right?
Correct. Exactly. That's all.
Right. Yeah. So, so you are making it pass through a second Stern-Gerlach setup, which is making an angle theta with respect to the original one. Okay. And then when you say that you have an E1 here at the other end, so you are seeing what is the projection on the E1 there, right?
Maybe, yeah, so that's what, so this is, I said it in passing in between. Each of this is a Stern-Gelac setup in itself. When I say there is an observer, in principle, I need a whole setup to get that. I cannot make G1 to project in that, so there is a whole setup in there. So if you want the best way, like I did, just for simplicity, I removed this. Like all this E1, when I'm saying that there is an observer, in principle, I should put in an E1 here. So that's another setup.
Yeah.
Just for simplicity, I removed that. So that should clarify. And then I say that, okay, then I have these two beams, right? E1. So maybe that's the confusion, right? I have, so even this, to select this, I have an E1. There's three Stern-Gelac setups being used to do this.
I'm just trying to understand. So you have this G1, G2, G2, which is a oriented Stern-Gelac setup. And now we are saying that so when you are putting an E1 here, so you are selecting one of the beam and saying what is the chance that it has a component along E1. That's what you are asking.
Right. Correct. Exactly. Yes.
Right.
Yes.
No, but you are selecting which one. So you are splitting initial E1 into two G1, G2, right?
Correct.
Now, when you are putting an E1 at the top here, I mean after that, so you are taking either G1 or G2, and then asking how much of it has got an E1, right? Am I right?
Exactly. Yes.
So you get the result as 1. Whether you would ask for E1 or E2, you would get 1, right?
Let me summarize this better, maybe. I think instead of this whole table, hopefully this helps. So we have this piece here, E1. So these are 3 G1, G2, and this E1, E2, G.
Shajesh, just a minute. Let me pose my question more clearly. Before you move that, so the first one you will have 2 beams, right, along E1 and E2.
Yeah.
This will
So
give
I select this.
No, in the first one he has closed the E2, so only
fine.
E1 will
Okay,
go.
okay. So you are selecting E1 from the first, right?
That becomes the source. After that, you say, "Oh, this is the source."
So that's your E1. No.
This is fixed. This is also fixed. Let's say, right? Let's say these two are fixed, right? In the current setup I'm building.
Okay.
Here I have the choice of first doing this, and the second I will do the same thing, but keep this the same. But this I do not make a selection. Does that help?
Okay, so you are okay. So in the first setup, you have crossed out the G2 output, and you are taking the G1 output and asking and putting it through the E1 E2 apparatus, right?
Correct.
And you are selecting E1 from that.
Correct.
And your result is 1.
In this case, this will be 1. In this case, this will be cosine
theta. Yes. Cosine 4 theta. Yes. Okay. Yeah.
And the way one wants to look at it is that, okay, in both cases, it's going through the same magnet. In both cases, this is going through the same magnet, right? This is a magnetic field. So the idea is that there is a magnetic field. This is the same magnet. This is actually going up and down. And you're selecting this. just because I peeped through this to find out what happened,
No,
that has changed the
Yeah,
changed
yeah.
the
Still, but so I have also now, if I have to compare these two, which you have drawn, so in the
Yeah.
in the first case, in the first line on the board, the first kind of experiment, you're starting with E1, and then it has two outputs, so G1 and G2, and you are selecting G1, right?
correct.
And then-
Selecting G1 here this will be like this. So here this has been selected. Right. This
Exactly.
has been selected.
Now the G1 you are subjecting to E1 E2 apparatus, right?
Correct.
And you are asking for E1. Now in the second case, since you have not selected G1 and G2, G1 or G2, you are both the beams are allowed to go through. So
Yes.
your E1 E2 apparatus, where are you putting it? To which beam you are putting it?
So now I'll put this again on this. Oh, I think your Christian you're saying is, yeah, good point probably. So I am
I think it is a
Yeah,
little bit simplistic to say this way. I think you are going to put probably, if you want to think of it as in terms of like two separate beams, you're probably putting the apparatus on both of them, calculating and then adding all the probability of what you're getting outside. So you have to get the even projection on both of them.
No, I suppose it's
No,
putting the
I
apparatus
wanna
in one of the two, not both.
No, I'm putting both, I guess, right? So this is whatever this means, right? And I'm actually putting this through the new setup, right? This is my E1. So this is E1. Right? This was G1. Like this is just so that, like I'm saying, but I have to put both beams there.
But
Which
how
is
did you
so notice.
So no, so how do you manage to convert the two beams? Because that's again a measurement. You have to have a mechanism.
Yeah, mechanism. Yeah.
Which is again a measurement.
Not necessarily, right? Let's see. Yeah, how do you actually mechanically do this?
You will need a magnetic setup.
No.
Actually, why magnetic
have to
setup?
rotate.
Yeah, why magnetic setup? It can be like whatever we used to do with the cathode ray tube, that kind of cross electromagnetic.
With light, I can imagine you just have to bring the light back, right? But with this magnets,
Yeah, you have a charged particle here, electron.
yeah. So I have this. So yeah, I cannot imagine directly, immediately how I.
I mean, would
bring
you be able to
back.
use another magnet, like just switch the north and south pole and do it in like a symmetric way?
Yeah, but that would still amount to a measurement, right? Because
I
you're
think,
Yeah.
but that would be an interaction, not a measurement.
Exactly.
Because you're not blocking anything, correct? So
Yes.
it'll be the
Yeah,
same.
I would think that you have these two beams that has gone very far away, and somehow you have to bring them back somehow, right? And you would say that, oh, if since they are charges anyway, the moment I try to orient them, you're putting in some field in there. Yeah. Not sure. Yeah, how to achieve this practically? Not sure. Yeah. Because this is a.
But then in that sense, one can clearly see the distinction between the, there is more fiddling with one beam than the other beam, right? The fiddling with the beams are different in the two experiments. They do not go through exactly same amount and same kind of fiddling, right? In one case, you are singling out, you are blocking G2 and only having G1, and then you are letting the G1 go through E1. I have no issues. Okay, that's one way of going about it. But in the other case, you have both the beams in the G1, G2 directions. Now, through some mechanism, so my point is that in the two different, the one set of experiments where you are not making a selection, and in one you are making a selection, the beams are going through different histories.
Correct. That's exactly the word. Yeah, histories. Yeah. And is it possible to wipe the history? I think that's the way to look at it.
And then, I mean, I think because I don't really, I mean, of course, the distinction between this interaction and measurement is, I mean, here you have defined it, but I'm not willing to believe that, there is no measurement in one and there is that there is no measurement in both. It's hard for me to, because the history is different.
Yeah. I'm not giving this as a complete, probably an answer to this. Suppose, okay, just thinking along your lines. Let's say that the beam is just sitting there. Like I move the magnet. Like all these silver atoms are just, because this is what we will do with an atom, right? There is a two-state atom. It can go up and down. And in that case, there is no motion necessary. So I'm wondering, okay, what will happen if you were to actually bring the magnet close to the source instead of actually making this beam really move in. But probably that's all. This is important. So yeah, not sure. I don't know. Let me not. I'm just thinking that, okay, move the magnets instead of, but I don't think that's a clean answer. Yeah.
I don't know. I mean, maybe I don't know. I think I perhaps don't understand. I mean, this. I'll have to. I mean, I see what you're trying to say here.
Or maybe, okay, maybe here is the point. I think remember that this was for intuition purposes, correct? The setup of the Stern-Gerlach itself is for my intuition. I wanted to have a physical feel for what is happening. But the algebra here has this feature that what you do here, like whether you project or not in between, changes the system. And this is the algebra we use to understand quantum mechanics. So whether how you set this up is different, but this feature will be there all the time. Maybe that's, if you take it in that sense, that might help better, right? Instead of, I agree that I don't have an answer to how you get this setup done, but if we use this algebra, then that has this feature in here, that whether I select or not, that changes my answer. And that's a that's in a sense a mathematical fact there.
Yeah, no, I understand that this algebra has this particular feature built into it. My concern is that this algebra is supposed to reflect the reality. It is actually a statement about reality. So suppose if I am not able to realize it through experiments, then it's a abstraction in mathematics, pure mathematics, where it's a mathematical reality, but all mathematical realities did not correspond to physical reality.
True.
All mathematical truths are essentially relations between logical structures, right?
Yes.
But not all of them need be realized in physical systems.
True.
So I should be able to perform an experiment that should realize this algebra. So I mean, of course, there is some understanding, but I actually am not able to. Or maybe does it help if we suppose put the identical Stern-Gerlach to both the beams and then add the results to both of them? Does it?
Yeah, but
add the probabilities for both?
I usually, I mean, the actual physical nature of that, I'm not sure. So I mean, the way I simplify, and actually it is. I mean, and if you really look at the setup, like that is a photographic plate, and the beams do separate in space. right? That's pretty
Mhm.
much the quantization if you want.
Yeah.
And then you bring it back. I don't know. Yeah. Yeah. Not sure.
But when you bring it back, would it not be amounting to changing the state of the system? Because, you know, moving them away through a Stern-Gerlach apparatus is essentially, you know, it's a action upon them. Okay, you are defining your measurement to be only when you make a selection. So from your
Yeah,
definition, you are allowed to do that.
I mean, just for argument's sake, the way I will put it is that we are all talking about the magnets, right?
Yeah.
So the actual magnets there, the orientation of that magnets. Even in this beam, the only thing we are interested in is that this is the magnetic moment mu now, and that is the magnetic field B, and it's rotating about it. It doesn't matter really where physically they are, it's just that orientation that you pick. And in that sense, maybe one can argue that, but I mean, that will be just for the sake of argument. I've not really thought about it so much. Yeah, so maybe that physical movement doesn't really change as far as you can keep those orientations with respect to the magnetic field.
Isn't this like
That's the
thought
purpose.
experiment, I think Feynman lectures, right? I think they have this designed experiment, like, oh, the way you can bring the beam together and go. Probably one of the volumes has this like imagined experiment and modified Stern-Gerlach experiment, and how you bring the beam together and then make them go. Wasn't there a discussion?
I think volume 3 has, I remember now vaguely, there is a pictures of being coming together in volume 3, because Feynman discusses a series of Stern-Gerlach. In fact, he builds everything in terms of this two-dimensional, two-state quantum systems, right?
Yes.
One can even motivate the need for the Hilbert space to be in this case, two-dimensional complex over a field of complex numbers. Even that can be motivated through this, that you don't have a real, it's a complex vector space. But I do remember now that Prachi has told, there are these diagrams where beams are merging together in Feynman volume 3 on quantum mechanics. So I think it is, Shajesh, I'm not doubting. I mean, of course, everything that you're saying is correct. I mean, there is nothing, I'm just trying to understand for my own.
No, I don't have an answer.
No, but that is, I completely agree with Rishi. Like a first-time reader, as a first-time reader of anything I studied on quantum mechanics, I was like thoroughly confused. And at that some point you say that, okay, this is making an interaction, but not a measurement, and this is making a measurement. And that's the difference.
So I think that perhaps, what I feel is that given Shajesh's definition of, which also John pointed out, that you call measurement only when you are making a selection. In that sense, if the treatment is democratic to both the beams, then you are not essentially changing the essential character of the beams. Okay, so you are not really fiddling with the beam, but I mean, because at some point, I mean, these distinctions have to be made. If you want to make a concrete statements, then one has to define what constitutes a measurement and what does not constitute a measurement and a distinction. And I think if one sticks to the definition that Shajesh gave, that measurement is when you make a selection. So as long as you are not making a selection, you are allowed to play with the beam as long as you are playing this democratic. You are not.
But the same question, it used to baffle whatever. Like you are being democratic and everything, even then there are magnets interacting with the beam. So, but the only thing is that we are not seeing when they are doing it. And in the other case, we are seeing it when it is happening.
And actually,
or maybe just to like summarize whatever you guys have pointed out. So this is the mathematics, and how do we physically realize it? Is there a very simple, clear way of realizing it that will help? this
Exactly,
doesn't really do the job. I don't think so. So is there a system one can, or even if it's a two-state atom, like can we think of a two-state system where we really do this and it comes out? And I would think that it is possible because yeah, first I just have to come up with a measurement, right? G1 and E1. First I had to make the angular momentum in the x direction of an atom and then measure it in the y direction. Probably that might do the job, but I don't have that clearly in mind yet. So maybe that's the way to look at it. So think of an atom and first measure it, the x angular momentum x is measured, and then you measure the y angular momentum, and this feature should come up there. But yeah, but the intuition I gave is for the Stern-Gerlach. Yeah, so maybe come up with a better
But
better
so
intuitive.
Shajesh, I think, I don't know, this measuring x first and then y, angular momentum, but then that the order would matter because the x and y, they don't, Lx and Ly
Correct.
don't commute.
Correct.
So then
Correct.
you're making a selection first for x and then for y, and first for y and then for x. It's not quite the same because the Lx, Ly don't commute.
No, see, that is where I think that probably I can justify. Let's see. I typically look at it like this. Let me try to answer that. And I think of Stern-Gerlach that way, but maybe this helps. I mean, this also might have drawbacks. So let's say, let's visualize just one magnet, right? So this is the magnetic moment, right? This is the mu. If you want, this is proportional to L, right? So this is L,
S.
right? Yeah, S. So yeah, S is better. S, right? And let's say this is the magnetic field we choose, right? That's the first, and this is now making rotations. So this is actually rotating, correct? Spinning. So this is spinning around the magnetic. Yeah, precision of this spin, exactly like a top, right? So there is a precision of the spin about this magnetic field. So when we say that we are measuring this this angular momentum, we are basically measuring only the LZ, right? So we are now by LZ, I mean in the magnetic field in this direction. So I'm just measuring this component here. That doesn't really mean that this this magnetic moment is collapsing on that. This is still keeping on spinning, right? The only point it does is that are you spinning in this direction or are you spinning in this way? So this keeps spinning around that magnetic field. So that's a precision that is happening. And when we ask the question that is it aligned with plus or minus, is it in the top cone or on the bottom cone? But it is doing its job of spinning, that's all. And now let us say that oops, that's my alarm or something. Yeah. So now let us, I come and say that, okay, this is keeping on doing that. Now I change this configuration and I change my orientation of my magnetic field to B. Right? So I first measured LZ and I asked how many are in this cone and how many are in that cone. And then I suddenly, in a fraction of a second, I flipped my magnetic field. Everything was spinning fine. You pick an instant where this was doing, let us say, when I flipped, it was somewhere here. Correct? One of the magnet was at this point here. And that's my magnetic field. Now it starts flipping, going in this direction. So this is the rotation. So it's instead of precessing and about this magnetic field, now it is precessing in that way. And that's decided by when you pick this. Right? And this is going so fast that if you do not give it enough, if there are millions of them, they are not at all oriented in a sense that they are all not in sync at all. And at some random time when you make it flip, half of them will be here, half of them will be there, even if they are all in the top cone, half of them are here, half of them are there, and they all will be somewhere here. So there will be two cones that you can form. Can you imagine that? So let's say that first you make a choice of being in the top cone, and then, but it's not very clear where on the circle they are. When you flip it, the probability is that half of them are on this side, half of them are on that side. Accordingly, there will be two cones there. So you flip them around that. And now you again flip it back, the magnetic field there. Again, they will orient it back. And now again, when you flip it, they are somewhere here. So they won't come back in that same place again. And now let's think of your question as to, let's say that I select my LZ, and if I were not to do anything, if I don't make this selection, so one is that if I select the first top cone and then the right cone, and then I bring it back, that is one system happening. But if I do not, all the magnets will come back up there, and will it bring back the same? I can't imagine that. Yeah, one has to do that carefully. But does it roughly give a hint of what I'm thinking along? I cannot completely. I cannot
When you say
completely
half of
state
them
the-
are here and half of them are there, you're of course talking about the number of electrons, right? No.
Yeah, so again, what I mean is that, so let's say that I select this cone, right?
Let's be clear about certain things. Okay, the first selection is not a selection. That's the input.
Yeah,
So
that's the
whatever
input that-
number passed
by
through
that
the
I
first
mean
selection, whatever number passes through the first selection will be called 100%.
Yeah, so they're all in the top cone, let's say. I selected the top
Yeah.
cone,
Exactly.
correct?
Yeah.
And now I say that in this top cone, there are a million of them, and they are all on the circle somewhere. The head of the magnetic moment is somewhere on the circle. I don't know where they are.
Yeah, that we
Right.
get it. And then you flip the cone and 50% will go from that selection.
Yeah, and now when I flip it, so they will either be on this or this, correct? So they're on this or on this. So they're here or there.
So 50% will go on this horizontal cone, and then you are taking the source again and you're flipping, and 50% of that horizontal cone will go back to the top one. So you say 25% is the probability getting it.
Correct. But I think the question then comes out, how do I select this, right? So this one, I don't know how I selected that either. But from this point, how will I separate this from that? Is there a way to, probably in atomic physics, like we have to think in terms of atomic physics where we want to filter this out somehow.
Probably you just block the beam somehow. I don't know.
No, Shajesh, so what are
That's
you
what
saying?
will
How
have
do
this
you?
problem, right?
No. What are you saying? You are saying that how do we select from the top cone? How do you split them into the two?
No,
First
no,
time
That I
no,
did it-
no,
that
Rishi,
I did
that's
it
not the
by-
problem.
That I did it by the magnetic field.
That
First
is
I
easy. Back.
magnetic field,
Mhm.
and then I changed the magnetic field to this direction, and now they are in these two cones, correct?
Yeah.
And but now I want to select, like I want to select only this. And that selection, how will I do? I'm thinking.
No,
Like when
you're
you are doing the back cone again, both the front and back of horizontal can give the top, right?
Yeah, but so you are no. The point is
So,
without making a selection. Yeah, sorry, John is saying something.
no, go, finish, please.
No, so without, I mean, if you block one, say minus X, you block and keep the plus X, that's straightforward. And then you measure that. But now when you're not blocking, that's where the challenge is, right?
Yeah,
Yeah.
why can't you get down facing? Like using this picture. I mean, so if you again put the field in the up, like why can't you get it down? Like you're in.
Yeah, exactly. So now when I again flip it back to the magnetic field there, there might be this somewhere here, right? So this can come in the bottom one, isn't it?
Okay, again, guys, I think
yeah.
Shajesh should not draw pictures like this. Can you make a vertical cone, then a horizontal cone, and then back again a vertical cone? Okay.
So I have.
And we will put them together in our heads.
No, that's okay. So this is first selection. So that's BZ, let's say. Right.
Okay. Now you go to the horizontal cone and make all of it.
Right.
Yeah. So you're, yeah.
BX. So half of them are going like this, half of them are going like that.
Yeah.
And
yeah, and then you put the top cone again, because that's where you want to go. Like, I mean, you are having an observer which is even, and you have an observer, no, you have a source which is even, and you want to have an observer that is even. Like this front and back should be considered zone.
Wouldn't it be correct to say that both are there?
Which one?
Like now, this one, when I take a snapshot, I can start going in circles here. So there'll be some of them in this one and some of them in that one.
Yeah,
right?
but you are only looking at whatever is in the top cone.
Yeah, there'll be.
Yeah,
Yeah,
but
how many?
before the blocking, so I think, okay, so if you measure it in the BZ direction, I mean, if you measure in the BZ direction, then like before the measurement, you'll have both cones. But I think if you don't measure in the BZ direction, if you just have it interact, then you'll only have the top cone. Because you'll have a probability of 1 for all them going back to the top cone. Is that the way? So, I mean, before
Yes.
measurement, like they would like even before measuring, like we could see all of them being in the top cone. Like kind of in this
But
space.
Shajesh,
Yeah, I think overall what, 1 second, Roger. So overall what I'm getting is that it is easy to, when we make a selection, it's like saying we are measuring, like LX is measured, LY is measured, but not having a selection seems to be very hard to realize, right? Is that the point?
yeah.
Like how do I have this system happen? Right, I'm putting a magnetic field, but so it's, and even in a polarizer, I'm having the same difficulty. I try to do this with a polarizer, like just this light going through a polarizer, and we have. Say that again?
That was my next question. Like analogy with the light is the best thing that one can do here.
Yeah, but there also I have this problem that what do I mean by not selecting? Like, how do I have a polarizer? It has to go through the polarizer, but not select. And it seems like not selecting, how do you physically realize it? Like,
wouldn't you, in the polarizer case, wouldn't you say that you're just passing it through a transparent film? That's it.
Yeah,
not selecting.
But then that's not doing anything, right?
That's identity. That's not polarization.
But that's what that's what you want to realize. Identity, right?
Yeah, but that's I agree. That's, I mean, mathematically that's true, but that's true. That's like saying that not selecting is not putting the magnetic field. Then it's sort of trivial, right? That's like you don't do anything.
And Shajesh, here, from BZ to BX, you have made a measurement, right?
Yeah, it seems
now,
like you made
now. So, once you make a measurement, then all the previous history is erased, right?
That is
there is no memory.
If they're complementary measurements, not any measurement, if they're X and P, for example, if they're complementary, then it will be wiped out.
Yeah, but then
all the history.
Z and X. So your LZ and LX are.
They're not complementary. Yeah, they're not completely. Angular momentum is not a two-state system, right? It's not like positional momentum. Not sure if completely
But
wipes it all out.
they don't commute. No, Alex and LY, they don't commute.
Yeah, they don't commute. They don't commute.
So the same thing applies to them.
Yeah, I agree to that. Yeah.
Same logic. So then
But that is all like once we
Just a quick clarification, Rishi, I need to understand this. What do we mean by commutation relation? Like, is it, like, just remind me, does it mean that you can perform the operation anywhere in space, anywhere in time, or it has to has some condition of simultaneity or something else?
Okay, so what is meant by non-commuting observables is that if you perform a measurement of, say, one of the non-commuting pairs, okay, then the system will collapse with the eigenstate of that, and whatever is the previous history of the corresponding pair will
gone.
be erased.
It's gone. Yeah. But when you say not commuting, it means that the other observable is simultaneously not possible. Is it? Is that what you want to say?
It does not have. So the system cannot have simultaneous eigenvalues for both of them. You know.
Great. So if you do it later in time, it's a new system now, right?
Yeah, but the point here is, I mean, what is contradictory here is that if you start with BZ up and you are ending up with BZ up, okay, going via X, then why not BZ down? Because then it seems to have a memory of, up, and X, Z and X are, LZ and LX are non-commuting. So if you have, okay, but the point is that in between you have not really gone through. Yeah, the challenge that we are trying to understand is that how do we make a measurement that is sort of democratic to both? I mean, Shajesh said that converging beams, so that you are now trying to make a Stern-Gerlach measurement on both the beams. I understand Stern-Gerlach apparatus on one of the beams. Okay, let me put it in as straightforward plain English as possible. I understand putting my Stern-Gerlach apparatus on one of the beams. How do I put Stern-Gerlach apparatus on both the beams? I don't understand that.
Yeah. And I agree that I'm not able to come up with it.
And like what I mean, I haven't gone through the Feynman lectures, but the Stern-Gerlach that I've understood in the Sakurai, for example, there I clearly remember that Sakurai is first of all not perhaps trying to address this question which Shajesh has addressed today. Sakurai is trying to address the non-commuting nature of the LX and LY. So Sakurai has not really tried to put Stern. That's why in all these series sequential Stern-Gerlach experiments in Sakurai, the apparatus is put on only one of the beam, only one of the outputs, not on both. Yeah.
Yeah, maybe we should all go back and look at Feynman lectures 3 because that's the only place I see this.
Yeah, I see this converging beams. Feynman lectures or the similar thing is also, I mean, there is one more nice quantum mechanics book which follows the Feynman's path, Feynman and Sakurai path. But yeah, the Feynman is of course hearing from the horse's mouth. Feynman and of course Schwinger, I think definitely.
What is this is mostly from Schwinger's lectures, like Englert, like he has compiled Schwinger's lectures.
Yeah,
write the name on the board, Shajesh.
I can pull out the
Englert. I guess I'm not sure.
Yeah, these are your Feynman lectures. Nice.
Yeah, this one's right, Shajesh, 3 volumes.
Oh, Schwinger. These are Schwinger's book?
No. Englert.
Englert.
There are 3 volumes. There is only 1 volume, I suppose.
No, there are three very slim volumes. Lectures on quantum mechanics. Volume 1 is basic matters. Volume 2 is simple systems, and volume 3 is perturbed evaluation. Perturbed evolution. Sorry.
Okay. I guess I have only volume 1 then.
No, there are 3 slim volumes, very slim, about 200 pages each.
Oh, I think, yeah, there is part 1. No, I think it is, yeah, the same book is split into 3 probably. Yeah, there is part 1.
Yeah, it's possible that you have a single volume and I have a 3
Yeah,
These are lectures he gave at Singapore University, right? NUS or something.
No, this was okay. The one that I have is based on Schwinger's lectures in UCLA, and Englert was a postdoc with Schwinger at that time.
Oh, you're talking about the book by Schwinger himself, quantum mechanics of, what is it, that very weird, not weird, but unusual title, measurements or something,
Yes. I think I can look it up. What is this?
Yeah, quantum
do-
mechanics.
If you have it, like just
Symbolism
show
of
it.
atomic
show-
measurements.
Ah,
Yeah, but this
symbolism of atomic measurements. Yes.
Yeah, but this
Symbolism.
is
Yes.
not written by Schwinger. This is not written by Schwinger. This is, I mean, it's called edited by Englert, but these are based on lectures of Schwinger.
Yeah.
And
So basically, these are lectures of Englert that he gave
I
at
see.
Singapore University. And of course, he follows the Schwinger style and Schwinger's examples. He also discusses, it begins with the Stern-Gerlach.
correct. Yeah.
He even talks about Bell's inequality and all that at the very beginning.
Got it.
Measurement problem and all that.
Yeah. Okay. Yeah. Okay, cool.
But it's a very interesting point that you have brought out today. I mean, I've always heard about this, but I think this has brought out in a very, in a very clear and a very straightforward fashion. It's, I've never heard this in this clear and straightforward way. It's just that I need to understand exactly the
Physical
difference,
realization.
relation of these two. Look, I understand the algebra, but
Yeah. So yeah, the algebra is it's a good point that how do you realize the not selection, right? So that I couldn't come up with. Yeah.
I mean, hindsight, I realized that doing the algebra in quantum mechanics is so easy, but understanding was like really hard. Even to this date, I do not understand what these statements actually mean. And it's the same thing, Rishi, as you're saying, like, I mean, to make it physically realize, you have to have an interaction, but just because you're not watching it, its behavior is different.
Yeah, and I mean, I think there's, even if you could, I mean, maybe this question will get addressed if you could physically realize it, but I mean, if you track like the G1 beam, the one that goes through G1, if you just track it locally and somehow you could merge the beams together, then the components from that G1 beam will then, depending if you block G2 or not, I mean, it should be ignorant towards the fact if you block G2 or not. So I think, but what happens if you block G2, then it'll start, you could have it up and down. But then if you don't block G2, then it'll always be up. So I think there should be like some non-local effect that's happening. Because I mean, classically, if you just look at it locally without any non-local, or yeah, if you just look at it locally, then like there's no way for the G1 beam to know whether G2 beam got blocked after merging. So there's also some, I think there's some physical explanation that could also be provided for why G1 beam then splits up into two if G2 is blocked compared to if it wasn't blocked. How is that information how is the information about G2 transmitted to G1?
I guess John is alluding to entanglement, probably.
I guess, yeah, something like that.
Yeah. No, good point. No,
Okay.
I hear you.
But but you're not making an entangled state with these. I think you're having them separate. So
yeah. Shajesh, this is discussed in Schwinger's this symbolism of atomic measurements, right? Is it discussed?
Yeah. Yes. Yeah, this is completely probably one section of his first chapter, but the notation is slightly different, but it is completely, I mean, in principle, everything is in there. Yeah.
Okay.
And including the like wiping out the complementary states, how they wipe out the past, all that is clearly there in the first chapter itself. Okay. So it's he's basically building the whole thing. So he spends a lot of time in building the algebra, but essence is exactly this. Yeah. Only thing I've changed is the notation.
Incidentally, referring to the Prach's first question on the silver atoms, I think what I vaguely remember, I think we had somewhere that they choose silver atom because it has, of course, 47 electrons. So you have also 47 protons and then, some number of neutrons. So the atom is relatively heavy. So the trajectory, you can speak of the trajectory of the silver atom because in principle, any odd number of this thing could serve the purpose, right? But then we are talking about the trajectory and making two separate trajectories and all that. So on the one hand, we are talking about the components of the L or mu about the z-axis and the so-called in the old terminology space quantization. That how L is split into the up and down, which is a completely quantum effect. But then you also want to, so it's like tagging putting an electron on the classical body. So you have a silver atom which is relatively heavy. So the trajectory is almost governed by classical equations of motion, and yet the lone electron which is sitting at the top of it, we are interested in the projections of the magnetic moment of the electron along the plus minus z.
So that's basically how do you build a beam, you're saying? Yeah.
Exactly.
So
beam
direction of
and the
beam is
trajectory. And the trajectory is almost classical. It's a relatively heavy, so you can speak of because the force, the gradient of this magnetic field which will act on it, and it will move, and so you can completely talk about a trajectory in the classical terms and the displacement, and because the separation is purely in the physical space, right?
correct.
So one thing which has always puzzled me, and I think because I think I still don't understand these things a lot, is because so you have, of course, the spin is a very it exists in the internal space, right? The spin vector is actually it's a vector in some internal spin space. It's not in a physical space, right? And yet, for all practical purposes, you are dotting it with some vectors in the Euclidean space like B and although the spin is actually living in a complex vector space, in a Hilbert space, right? Spin is not a vector in the real this thing, it's a, and yet for all practical purposes, you are treating it as a vector and dotting it with the physical electric and magnetic fields are classical fields, right? And so I mean I have some discomfort about, because this x, y, and z of spin is not really, I mean it can practically behave like a vector in a 3D x, y, z space, but then the two components of spin, you require a complex two-dimensional Hilbert space to describe spin, right?
Yeah.
So I think that is something really, I think, and this I think is something very deep, because ultimately, when you look at it in the group theoretical terms, you have the two quadratic Casimir invariants, which is the mass and the spin, right? S square. And spin, that actually is very non-trivial thing, the whole, classification of quantum states, according to their behavior in the Poincare transformation, it splits into those 6 or 7 categories, right? Where massive and massless.
Correct. There is a distinction there.
Yeah, distinction there. And then you define this Pauli-Lubansky pseudo vector, right? And I think spin is also, something which comes in the way of, because on the one hand, it's something very fundamental to, I mean, this theorem of quantum field theory that, all you have the spin half, I mean, fermions and bosons which follow different statistics. Okay. And that's a very fundamental theorem of quantum field theory. But then, you have this supersymmetry where you have a merger of, you have a basically in the Okay, so if you look at what is the most general symmetry of the S matrix, then it's the Lorentz group. If you have generators with commutation, if you have a generators of the transformation which follow commutation rule, okay, then all your multiplets are among the similar spin. I mean, you cannot have a multiplet of two different spins, right? But if you are willing to relax this condition that all your generators have commutative algebra, if you are willing to admit spinorial objects, and when you are willing to admit anti-commutator possibilities, then you can have this mixing between the different spin particles. Okay. So in supersymmetry, you can have a superspace and a a super multiplet where you can mix spin 0 with spin half. Right. So what I feel is that I think how exactly spin enters and the relation of the spin with the ordinary Lorentz space of the Lorentz 4-dimension and the spin, I think it's very something very deep. And of course, people who are doing deep string theory, they perhaps understand, people like Witten and all that, because they have found some connection between supersymmetry and Morse theory and all that. But ultimately, these things have deep connections with, if one studies about quaternion and twisters and all that, then as Penrose has developed this entire thing in a complex. This twister space is complexifying these things, and then you can, so there are deep. I mean, the spin. I feel that the spin's relation with the rest of the thing is very non-trivial, which I've never quite understood.
Agreed. Yeah.
Yeah, I think maybe, I mean, the Lorentz group like decomposes, and you could decompose a metric that you could Lorentz transform into two different triads. So I think the Lorentz group like decompose into SU2 cross SU2. So
yeah, the Lorentz group is SU2 cross SU2. Yeah.
So yeah.
So yeah, the spinors are the most fundamental representations in terms of which you can build all the higher representations. The 0 half and half 0. Yeah. So the Lorentz space has a very non-trivial relation with the complex SU2, I mean. So, I mean, anyway, there is SU2 and SO3, and SU2 cross SU2 is SO3, 1, right?
So maybe I should pose this question. What do we mean by space? Like when we describe something mathematically in some space or other space, what is its relation to the real space? Or what, I mean, is there something which is a physical space and something which is like purely mathematical space? Or like, I mean, there is some property in that mathematical space that has a kind of manifestation in the physical space. Like, how do we think about it? Like, we understand mathematics of certain things very well, but then of course there are observed phenomena that is occurring, and there is certain properties that needs a description, but all of that needs to be done in some physical space, right?
So I guess maybe, I mean, the way like the way it made sense to me was just like spin is just a unitary representation of SO3, like just three-dimensional rotation. So because that, like, since we're doing quantum mechanics and we're working with the states are invariant under unitary transformation, then we also have this additional component of the unitary representation of three-dimensional rotations. So I don't think that answers your question, but yeah, I guess that's how spin kind of comes in calculating the total angular momentum, because we have a Hilbert space, and that's a projective space. So a projective Hilbert space in quantum mechanics. So
I think if I understand the Prachi's question, the way I understand your question, Prachi, is that if one looks at it, purely mathematically, okay. So you have a SO3, which is a rotation group in 3 dimension, and there is a homomorphism of this SO3 with SU2, right? It's a 2:1 SO3. So you can do everything that you can do for SO3 in terms of a complex 2-dimensional space. So it's just a mathematical way of doing things in SO3 and SU2. Now the question is that, so one can look at the question of the representations of the unitary groups, and SU2 has this, the smallest representation is by the spin half. Okay. Now the real question that bothers me is that, so you have a Lorentz group which is SO3, 1, and SO3 is a subgroup of SO3, 1, right? Rotations in pure 3-dimensional space. Okay, so it's a subgroup, and you have objects living in, so you have a Minkowski space, which is a physical space. You have a 3-dimensional, subspace of the 4-dimensional Minkowski space, which is a physical space, and you have physical objects living in the 2-dimensional space. Okay, but the spinorial representations, they purely follow as mathematical objects, and had it not been for the existence of electrons, okay, which are spinorial objects, we would have spoken of SU2 as a purely mathematical fantasy. Okay, then the question is, why is it that representations of SO3, like ordinary vectors, you could have displacement, acceleration, force, momentum, electric field, magnetic fields. These are all representations of your SO3. These are all palpable in the physical universe. But the representations of SU2 live in a complex 2-dimensional space, which is different from the physical space. Okay. And why exactly, I mean, it is one thing to say that your SO3, 1 is SU2 cross SU2, because you can build all your representations of Lorentz group from SU2, right? The 4-vector representation, your spin 0 representation, your spin half, say you can build everything. Okay. So your most fundamental representations live in a complex vector space. But the physical world is a real 3-dimensional space, right? So we know what is the mathematical relation of the Lorentz group with the complex SU2, but then this question always remains that okay, see, even quantum mechanics happens in Hilbert space, but electrons move in physical space, because Hilbert space is only a mathematical description of the quantum systems, right?
I think one can say that if you were to confine to SO3, then you cannot have L equal to half, right? Angular momentum half is not allowed. So yes, it is all integral. It is all integer spin. So the moment electron came, as Rishi pointed out, the moment you want to explain electron spin, there was only one room there that, okay, you go to the covering group of SO3 and that's SU2, and that explains it. So experimental observations required you to go into SU2. We don't have anything better, that's all.
Okay, so I have a perspective to what Prachi is trying to ask. And like whenever I teach quantum mechanics, I always discuss this point of view. I think the challenge here, is more philosophical than physical. Okay, by philosophical, what I mean is that it's like for example, okay, let's forget about this. Let's talk about the wave-particle duality. Okay, I mean, people find it very hard to understand how could something be a wave as well as a particle, right? Now, I think that difficulty stems from, ultimately we want to map everything that we discover, okay, about the physical world in terms of how we make sense of the physical world, right? We want to make sense of all of our discoveries using the vocabulary that we have acquired through classical interaction with the world, right? So our vocabulary is developed from the classical interaction, where in the classical world, the world splits into two distinguished entities. You have objects which are purely waves and which are like sort of spread in space and time. And you have objects like particles which have a localization. And there is a mutual exclusive attribute to this both, that you cannot have something in the classical world, that you cannot have something which is simultaneously both. So this mutual exclusivity of waves as waves and particles as particles, this exclusive understanding of these two entities is arrived upon through classical interaction, okay, with the classic macroscopic world. Now, we cannot expect that the same vocabulary, now as you go down the stairs of, you scale down the stairs of dimensions and go to smallest units. And now you say that, okay, am I entitled, that I am entitled to use my classical vocabulary to describe the most fundamental entities. I think to me, this question itself is actually farcical and ridiculous. So the way I put this to my students is like this, the example that I give them is like this, that suppose, I have a class of 50 people and I conduct a test. Okay. I'm sorry, I'm taking a little longer than I'm allowed to speak, but I just want to convey a perspective. Okay. I have a 50 student in the class and I take a test. Okay. Now different people will get different marks, right? And there will be an average mark. Suppose average is 35 out of 50. Okay. Now, to an outsider who does not know the distribution of marks, okay, I give the person average and ask him to predict the distribution of marks. Can he predict? No. Knowing the average, you cannot predict the distribution. But if I give the individual marks, if I give the distribution, of course he can come to the average, right? So if you know the details, you can average. But if you know the average, you cannot come to the distribution, right? So the way I understand this challenge of quantum mechanical questions is that, our macroscopic world is an averaging of fundamental entities. It's an average macroscopic behavior of fundamental. So we know the average. Okay. So our classical vocabulary is built to understand this average. Now, if you expect that, I have this vocabulary which clearly distinguishes between waves and particles, and I expect that the same conception to hold true for the fundamental entity, it will be as farcical as trying to predict the marks of students knowing the average of the class.
Yeah, but Rishi, that is the same thing I'm saying the same thing. So the point, we are back to the square one here, the thing that you raised in the beginning itself, that a spin lives in certain space. And then we take a dot product with the classical space vectors, and you never, you raise the question in such a fashion. So this is what I mean to ask, or lead to ask, basically, is that, whatever is the space that we say that those tiny particles are actually living in, or whichever down the stairs we are trying to describe, is actually a real space. It's actually a physical space. Why do we say that complex space is not a real space? That's
so it is as physical as it can get, but it did not match with our perception of the physical world, which is, but then the challenge, the problem that I would like to pose here is this, that then, we have to be able to build, the real challenge is that, can we build this picture of the classical space starting from the most fundamental representations? Okay.
Yeah.
Just as, quantum mechanics is still able to, in principle, able to explain the macroscopic behavior, right? In principle. But because in the sense that, we are able to see the Newtonian mechanics